Thank you so much, Cyril, for the invitation and also for the very nice introduction. So can you see my cursor? That's my question, I guess.
Yes, we can.
Okay, perfect. So I'm going to talk to you today about quantum entanglement across cosmological distances. And this work is based on a whole lot of work. As you can see, I tried to not forget any of my collaborators and so on, but mostly this is based on this paper that I wrote early last year, and this one I wrote with Omar, who is a student at McGill, and Robert Brandberger, and a paper which we just finished with Arjun Pereira and Jaime Calderon at Edinburgh, and this is yet to appear on arXiv. It should very soon. Okay, so what's the outline? And I'm sure all of you know inflation. I mean, this is an audience which knows inflation. Probably many of you know it much better than me. But just to give you a very brief introduction, this is an early phase of accelerated expansion, as we all know. And this is what inflation does. Like, you take a tiny patch of space and it blows it up. It makes it the entire universe. And that's why, you know, it solves all the standard cosmological puzzles and so on. And the point is, it not only solves this cosmological puzzle, such as the flatness problem and the horizon problem, you know, all of these monopole problems and things like this, but the most remarkable achievement of inflation is that it can explain the late time inhomogeneities, which we observe in the CMB or in large scale structure, as coming from quantum vacuum fluctuations. And that's kind of a very remarkable feat, as anyone who is familiar with this calculation can vouch for. And this is, I think, a picture which I have to show when I give a talk about inflation. So we are really thinking about what happened here. Like, you know, sort of, this is going to be my talk about inflation and about even an era before inflation. So what do we know about inflation? We know that it has to have energies between these scales, and these are set by, the upper bound is set by our non-observation of the tensor to scalar ratio. So it's set by the upper bound on R, so a non-observation of primordial B modes. And the lower bound is set by BBN constraints. But if you're ambitious enough, we can even ask what came before inflation. I mean, already, as you see, we don't, we have a general idea of what inflation is, but we haven't pinned down everything, because we don't know what the energy scale is. It can vary over a very huge range. So it's very ambitious to ask, can we go even further back? Can we figure out what happened before inflation? And the general idea is that even if you're not able to have a quantum theory of gravity yet, can we see whether from general principles it is even possible to have a UV completion for inflation? Or to put it differently, can we derive inflation from fundamental physics? So right now, whenever we talk of inflation as an effective field theory, we sort of postulate an inflaton scalar field or some other gauge fields or something like this. And we postulate a potential for it by phenomenological constraints or some theoretical biases and things like this. But can we sort of derive that effective action starting from some quantum gravity theory? Even if we can't be that ambitious, can we at least see whether such a program might be successful, or are there any obvious obstructions to it? And the reason, and it will become clear why I say that there might be some obstructions to it. So inflation, of course, gives you this very rare scenario where you have this nice interplay between the quantum scales and the larger scales in the universe, right? Because as I already mentioned, quantum vacuum fluctuations are the ones which are being stretched out and to create late time inhomogeneities. So we expect some extreme tests of quantum mechanics can be performed from observing data if inflation is to be true. And again, this is just to show how far we have come in terms of observations. This is the Kobe satellite, and this is Planck, and this is how well we have measured the CMB today. So the main part of my talk is going to be on this, like quantum phenomena. Two of the most characteristic things of quantum theory are quantum entanglement and non-local behavior. These are sort of hallmarks of quantum theory. So if there is, of course, any sort of non-local behavior, then we don't know, I mean, then any scale can influence any other scales. And we know there's a good description of Wilsonian EFTs which apply to everyday life. And how we can input theories about below some energy scale. We integrate out everything above that energy scale to give us effective field theories below that scale. And that description is usually very good. Does a similar description apply to inflation? That's the main question which I would like to answer today, or at least explore. And if not, what kind of a description is the more appropriate one for inflation? And I would suggest that this open EFT formulation, which I will of course describe later on. And this would be somewhat connected, even if not very rigorously, but heuristically to decoherence and stochastic inflation. And I will go through these connections later on a little bit. So what's the take-home message? If you fall asleep just after this slide, what should you remember? Well, what you should remember is that what can we learn about quantum gravity completion of inflation in particular from open EFT for inflation in spacetime? So in general, how much can we learn about quantum gravity by studying quantum field theory on curved spacetimes? And in this particular talk, I'm going to talk about quantum field theory on inflationary spacetimes. Does quantum field theory on curved spacetimes have anything to tell us, or is it so pedestrian that it can have nothing to tell us about quantum gravity? And I will answer this in the affirmative, that it does have something to tell us about quantum gravity. And at the other end of the spectrum, what role does entanglement play in cosmological observation? So if indeed there is some sort of quantum entanglement between modes of this fluctuating field, which I mentioned, these quantum vacuum fluctuations. So if modes of this fluctuating field are indeed have interactions between them, they are entangled, can I observe that entanglement? Can I observe some signature of that entanglement in the data? So that's the plan for today. That's the take-home message. Okay, so the first part is going to be about quantum gravity and inflation. So this part, I apologize to any quantum gravity people in the audience, because this might be sort of well known to you. And this is more for motivation purposes, if nothing else. So what are the challenges? Why do we even think that inflation might not have a UV completion? So let me change track completely and talk about what this program, which is known as the Swampland program, which came out of string theory, but is actually more general. And what is the Swampland? The Swampland is a set of principles which tries to demarcate between the landscape of string theory and theories which do not have good UV completions. So let's say you have a low energy effective field theory. A priori, the theory doesn't have anything wrong. I mean, it's not Lorentz violating or anything like this. So you thought this is a good theory, but it disobeys one of these Swampland conjectures. That means that although the theory looks fine from the low energy point of view, it can never have a completion into quantum gravity in the ultraviolet. That's what the Swampland is supposed to do. So this is, of course, a cartoon that, we have all these little landscapes, but there is a much, much bigger swampland around them. There's this place which, where so in other words, you have there can be a lot of low energy EFTs which do not have UV completion. Of course, that doesn't mean that none of them have it. Some of them do. And there are principles which they must obey in order to have UV completion. That's the idea of the swampland. So as I already mentioned, this is complementary to the string landscape. And originally the idea was the landscape is so large, almost anything goes. It has lost all predictive power. You can only do things such as anthropic principles, but that's not quite true, because even if the landscape is large, the swampland is much larger. So in other words, not every low energy EFT can come from string theory or some well-behaved quantum gravity theory. So what are these principles? And the principles, so these are some universal features of quantum gravity. So that's why I keep referring to this as quantum gravity and not string theory, because these are sort of universal features which one expects should be reflected in any consistent quantum gravity theory. So for example, there's this weak gravity conjecture, which, simply put, says that gravity has to be the weakest force. There's the distance conjecture, which says that, a field can have an excursion which should be less than order 1 in Planck units. And there's the de Sitter conjecture, which says, which I'm sure all of you are familiar with, that either the slope is large or it's tachyonic. In other words, you can't have metastable de Sitter.
Sorry for a very naive question, but I have a difficulty between the word must of the universal features and the conjecture word. If it must, it cannot be a conjecture, and reciprocally, I am a little puzzled by that. I mean, what is the theorem there?
Oh, right. So I was coming to this. So the point is, these are all conjectures, right? So none of these are proven. None of these are like a principle that has to be obeyed. Why is that the case? Because it's very difficult to prove any of this concretely. But there are different of these conjectures. Some of these are more tested, more rigorously tested, and there is a lot more rigor in deriving some of these from, let's say, more fundamental stringy principles or quantum gravity principles, and some are more heuristic and more out there and more sort of provocative, let's say. So I will comment a little bit about this later on, but in general, you're absolutely right. These are just, so the idea is that can we figure out some universal features of quantum gravity which low energy FTs have to satisfy. I'm not claiming that these are some God-given universal features which low energy FTs have to satisfy, but we have to make a start. And these, for different reasons, I'm just naming three, there are many others, which seem to be good features that come out of string theory. So let's try to impose them on low energy FTs and see where we get from there. But of course, that's just one part of the program. The other part is to prove these conjectures more rigorously, to show whether there's some underlying structure behind it. And I will talk a little bit about that later on. So you're absolutely right. I'm not saying that this must be satisfied.
So therefore, I understand that the sentence is not which must be obeyed, but which should be obeyed, something like that.
No. Sorry. Okay. I thought you said most. Yeah, now I understand. So this must is to say that the Swampland says that there are these features which must be obeyed in order to have UV completion. That's not to say the Swampland is correct. The Swampland program might be wrong.
Okay, I understand. Thank you.
Yeah. So of course, this is very powerful, as I already mentioned, to constrain the space of all low energy effective field theories. But there's an analogy here, a nice analogy here with quantum mechanics. So for example, let's look at the de Sitter conjecture. It says that we thought that low energy FTs could have almost any potential, unless the potential has some weird discontinuity or some topological defects or something like this, which is obviously problematic from mathematical point of view. Almost any potential, smooth potential, should work for, let's say, model building for inflation or some other cosmological model building. But now this de Sitter conjecture is telling us that no, not any potential goes. Like there are only certain sorts of potentials which would be allowed. So in this sense, there's some analogy with quantum mechanics, the early days of quantum mechanics, when things are not at all rigorous. People are just coming up with different quantization rules and different things which they think should be obeyed for a theory to be viable. But that doesn't mean that all of these are correct. I mean, in the long run, some of these principles might survive, none of them might survive, or something else might come in. But that's the program, that we try to come up with principles and then try to see how rigorous are these and how can we connect one from the other, and how can we connect them to low energy FTs. So one thing which I should mention here, because of thanks for the question for this, which is that unfortunately what tends to happen is the most rigorous of these conjectures are not the ones which are very interesting from the point of view of model building. So for example, the de Sitter conjecture is very interesting from the point of view of model building because it rules out so many potentials which we thought are important. On the other hand, there is this no global symmetries conjecture, which is probably one of the most rigorous ones. And I think almost any theory of quantum gravity would take that seriously. On the other hand, that's not so interesting from the point of model building. So there's a gap there. So one of the programs of the Swampland is to start with, let's say, the de Sitter conjecture and try to see whether can we derive it from one of these more rigorous conjectures. And that would make us believe in these more speculative ones a little bit more. Okay, so that's a general introduction to Swampland. But now let's come back to, okay, why do we want quasi-de Sitter space or de Sitter space? Because I just said that de Sitter conjecture rules out at least de Sitter space, at least metastable de Sitter space. So why do we want them? And of course, all of you know that there's overwhelming evidence that there are at least two stages of accelerated expansion. So let me focus on the inflationary era for today. And the simplest solution should be the one that we adopt, right? And the simplest solution is that if we have like a slow rolling scalar field with an almost flat potential, that does the job for fitting data. So, okay, we are done. We can explain the data. Why should we worry about quantum gravity completion? And this is, again, kind of going back to this question that, okay, maybe string theory says that there's no de Sitter space. Why should I bother as a cosmologist? And the answer is because inflation by itself is not enough. As I mentioned at the very beginning, we want to know what came before inflation. And in fact, there are works to show that inflation can't be past infinite. So there must be a surface on which inflation has to begin. And you need some new boundary conditions from some UV theory for inflation to begin. So what is the origin of the inflaton? What are the initial conditions for inflation? These are questions of quantum gravity. So if we want to answer some of these questions, then we should keep in mind what are the general guiding principles which quantum gravity is telling us. And that's why it's important to have a quantum completion. So just to answer this question, inflation is perfectly fine as a low energy FT. Why do we even bother thinking about its quantum gravity completion? Well, this is why, because it's not sufficient. It's not sufficient to go back as much as we want, and we are very ambitious. Okay, so let's say for a second now that the de Sitter conjecture is true, the Swampland is true. What does it tell us? It tells us that, as I already mentioned, not anything goes. You can't have whatever we want. And in other words, because we have an upper bound on the tensor to scalar ratio, it tells us that this epsilon, the first floral parameter, is very small. And this is related obviously to the V prime over V, which I showed you earlier. So that means that it is smaller than 0.1. So this kind of has a feeling that this is in tension with the de Sitter conjecture. But of course, this is not quite true because of many things. First of all, 0.1 can still be an order 1 number. But more importantly, there might be some fine tuning. Like if you don't find R in the future and we need to make C to be less than 0.001 or something like this, then that would be a fine tuning game. We don't precisely want to do that for the de Sitter conjecture. So in that sense, there is some tension. But how can we get past that? So did some work in the early days of the de Sitter conjecture to show that if you have some non-Bunch Davies initial state, essentially which violates this consistency relation, then things are okay. You can rescue inflation. And of course, other people figured out different ways of violating this. For example, using multi-fields and warm inflation, and maybe something on the brain and so on. Of course, I won't go into late time cosmology today, but if you're ruling out de Sitter, that's very bad for lambda CDM. In fact, it's also bad for quintessence models. And this was shown early on by Vafa himself, and then also by Robert and collaborators, showed that quintessence is also sort of in conflict with Swampland when we take observational constraints into account. And very recently by Aurélien also showed something similar. And in fact, it was shown by Lavinia, Robert, and others that almost all of the Horn-Deskey theories, I mean, this is a very strong statement, but many of the Horn-Deskey theories are in tension with the Swampland. That's not to say that these are all ruled out. That's just to say that if the Swampland is correct, then there's a problem with these theories. And of course, conversely, if one of these theories describe nature, then there's a problem with the Swampland or string theory in that sense. But you can always play games to get out of this. So theorists are very good at model building, and we played some games, and we can get out of this using this cubical Illian model where you can have C to be order 1. In fact, it can be exactly 1 and still obey current observational bounds, and even obey bounds coming from model independent bounds coming from Pantheon data. So that we showed in a later paper. So I won't go into details of that, but just to say that this is why the Swampland conjectures are very interesting, at least to me as a cosmologist, it's very interesting because it's telling me that low energy effective theory involving accelerating spacetimes, even if it is late time acceleration, can be somehow constrained by consistency conditions coming from quantum gravity. If these are true, this is a very, very exciting thing for cosmologists, right? Because we have a very big challenge for model building. That's the main goal. So I won't go into dark energy today. Sorry, let's skip that for now. So, okay, now let's come to this bigger, the elephant in the room, which is why should you believe the de Sitter conjecture? What evidence do we have except for Vafa coming up with this? So it's not quite so simple. It's not like, they just came out one morning with like, okay, maybe there's no de Sitter space. Of course, the main reason for this is there's an immense difficulty of constructing metastable de Sitter vacua in string theory. That's not to say there's a fierce debate about this, whether you have any or not. There are these very heroic attempts of KKLT and the large volume scenario proposals. But when you try to calculate explicit models, there's always one technical obstruction or the others to do with this uplifting from the ADS vacuum to the de Sitter vacuum and things like this. So there seems to be a lot of technical problems when one tries to do this. Some of it is highlighted in these papers, but there's a whole host of papers which go into details of these problems. But more importantly, as I mentioned earlier, the de Sitter conjecture itself can be derived from the distance conjecture. So the distance conjecture, you can of course say that I'm shifting the goalpost, I'm just going back to another of these Swampland conjectures. But the point is the distance conjecture is more rigorously tested in stringy constructions. And what was shown by Vafa, Gary Shu, Uguri, and Palti was that you start with the distance conjecture and you just assume the covariant entropy bound. So the Busso's covariant entropy bound, which we expect to hold for accelerating of de Sitter spacetimes or quasi-de Sitter spacetimes. And you can come up with the refined de Sitter conjecture. So that's kind of nice. That gives us a little bit of confidence in the statements. That this is not all like, hypothesis. Maybe there's something behind it after all. But there are other reasons as well. So for example, Diwali came up with this quantum break time for de Sitter. The de Sitter is essentially should have some quantum break time after which the classical de Sitter description should not hold. But there are also indications from approaches outside of string theory. And this was very interesting to me when I first looked at this. So at that time, when I looked at this paper, I was not working on the Swampland at all. And what these people showed, Turok, Lenners, and Feldbruch, is that if you start with the Hartle-Hawking wave function, at least for many superspace cosmologies, that's a good way to complete de Sitter spacetimes through this Euclidean instanton. And this was known from the 80s. And this is the very famous no boundary wave function of the Hartle-Hawking wave function. But what these people showed is that there's a problem to that. Once you introduce perturbations, there seems to be runaway perturbations. And of course, Hartle and Hawking also did perturbations. What the contribution of these people was to try to use the Lorentzian path integral and use Picard-Lefschetz theory to see which saddle points should contribute to the Lorentzian path integral. And what they figured out is that the right saddle points, which should contribute to have a well-defined semi-classical amplitude, actually leads to runaway perturbations. So the Hartle-Hawking wave function suddenly had some obstructions. And as I mentioned, this is completely independent of Swampland program, but it seems that there is some synergy here, right? There's a completely different approach to having quantum completion for de Sitter space. And that seems to have run into some problems. Of course, when you include some non-perturbative corrections, as I did with Martin, coming from loop quantum gravity in this particular case, you find that maybe some of these problems can be ameliorated, but there's a general picture here. And this is the picture, right? This is a very famous Hartle-Hawking wave function. And what one expects is that you have small perturbations around the mini superspace background, you'd get the Bunch-Davies vacuum. Instead, what happened was that the perturbations kind of disrupt everything, and you have runaway perturbations. And so you have inverted Gaussians and things like this. Okay, now all of these points are sort of quantum gravity points against de Sitter spacetime. Do we have something better? And this is not quite a quantum gravity point, but somewhere in between, which is that it has been long argued that at least eternal de Sitter spacetimes are inconsistent with having a finite entropy for de Sitter. And this is not to say that the de Sitter should have, this is not the same thing at all as the de Sitter conjecture, but this is just saying that de Sitter space should not be eternal. It should be metastable. It can have a very long lifetime as far as this argument goes, but at least it should be metastable. And this was seen from different arguments, like Susskind shows this from considering thermophile double picture, where Zakani Hamid and others and Tom Banks has been talking about this for a long time in different ways. So the essence of this argument is that we believe that de Sitter space should have a finite entropy associated with it. And that is inconsistent with having the classical symmetries of de Sitter for eternal time. They must break after a time. Only then will it have some finite entropy. Now, finally, let's come to a point which has nothing to do with quantum gravity at all. And this is a QFT point. And this is sort of the motivation for the rest of the talk, or at least for later part of the talk, which is, de Sitter space seems to be unstable when coupled to interacting QFTs. And this was advocated by Motola from 1980s and Polyakov also for a very long time, that if you have the de Sitter vacuum, which is the Bunch-Davies, let's say if you take the Bunch-Davies vacuum and you find that there's some particle production from the vacuum, and then the interactions of these produced particles lead to perturbations which break the de Sitter isometry loop. So in other words, let's say the classical symmetry of your spacetime is indeed P equals minus rho. Then you calculate the one loop correction with respect to your vacuum state, and you find that the one loop effective action does not obey P equals minus rho unless you choose a very specific vacuum, which is this Bunch-Davies. But I will come to that point later on. And if it doesn't satisfy the symmetries, what it means is that you have a discharge of the cosmological constant. The cosmological constant sort of leaks away into matter and radiation. And finally, very recent conjecture on these lines is this Transplanckian censorship conjecture, which I really think is an EFT argument. And of course, this comes out of the Transplanckian problem due to Jean Martin and Robert Brandenberger. And this also puts an upper bound on the lifetime of de Sitter and also inflation. Of course, as you see here, I talked only of de Sitter, but always in my mind, I have quasi-de Sitter or inflationary spacetimes in my mind. And many of these arguments, or in fact, probably all of these arguments generalize to inflationary spacetimes as well, because they're so closely related. Okay, so let me talk a little bit about these different corners of the Swampland. Like, what can we learn from QFT in de Sitter spacetimes? And this is a good point to stop and just ask this question, right? That why should we believe in any of these things that string theorists are telling us? Well, even if we don't believe them, let's just keep them in mind and then try to understand better things we know. For example, QFT in de Sitter spacetimes. Those are things which we think we know, and try to see whether we find similar effects which they are claiming should come from any UV complete theory just by looking at QFT in closed spacetimes. That's what I want to emphasize on. Okay, so this part is just saying that, you know, if you have, let's say you have P equals minus rho, as I said, does radiative corrections destabilize it? And this was shown in a paper quite recently by Ulf Danielsson. He called this quantum swampland. He used some arguments from usual QFT, but also from string field theory and so on. And the point goes like this. So the one loop effective potential can have de Sitter invariant term only when you choose the Bunch-Davies vacuum. And this is very nicely reviewed in this article by Jean Martin. And if you have anything other than the Bunch-Davies, there's a problem. But maybe it's not so natural to have the Bunch-Davies vacuum. And this is a very, very old debate, which goes back, you know, between Polyakov and Susskind and many other people on both sides of this debate. The way I will frame this question, there's many different ways of framing the question, why the Bunch-Davies might be not a very natural choice. But the way I will phrase this for today is that let's phrase it as a cosmologist, as an inflationary cosmologist. So Davies, we say that, you know, we make a mode expansion and we then trace the mode back in time until it's so blue shifted that its wavelength, its physical wavelength, is much smaller than the Hubble scale. So then we say that, you know, it doesn't feel gravity. You can forget about the de Sitter space and pick the unique Minkowski vacuum. And you do this with all modes, then you get the Bunch-Davies. So that's like saying that in conformal time, you take eta going to zero, going to minus infinity at early times. So all the modes would be well within the horizon. And that would be the Bunch-Davies vacuum. But of course, there's a problem with this, right? The problem is that inflation must have started at some scale. That's the problem. Our theory has a very physical cutoff. The cutoff is the Planck scale. We don't know what happened beyond Planck scale. So if that's true, we can only parameterize our ignorance, you know, above Planck scale physics in the initial state. Let's say we can say that it is some Bogoliubov rotation of the Bunch-Davies or something like this. But if you choose such a state, I mean, it doesn't matter what state, but if you choose any such state, which is not the Bunch-Davies, what you would end up is with what Ulf Danielsson calls the quantum swampland, because that would mean that now your one loop effective potential does not have de Sitter invariant terms. It doesn't have P equals minus rho anymore. You're breaking the de Sitter symmetry. And typically one argument against this is that, you know, de Sitter quantum no-hair theorem has tells us that the Bunch-Davies is a quantum attractor, that you start with any state and you will go to Bunch-Davies after some e-folds of inflation. That's true, but then the problem is if your inflation is short-lived, which is what I will go to next, then this is the problem, because you don't have enough additional e-folds to wash away all the effects of the initial state. So you still have some effects left, and that's kind of a teaser for the TCC. Okay, so as I already mentioned, the crowning glory of inflation is that, you know, we can explain this observed macroscopic density perturbations as originating from quantum vacuum fluctuations. And this was noticed long back in early 2000s by, as I mentioned, Jerome Martin and Robert, is that if you blue shift them backwards in time, it might just so happen that their physical wavelengths can become smaller than Planck length. So if inflation lasted for a very long time, then it might just be that something that we observe today, when we blue shift it backwards, originates from a sub-Planck or a trans-Planckian region. But that would mean that inflation is valid until energy range is much beyond Planck scale, which is uncomfortable, to say the least, as an EFT. I'm not saying that this is a conjecture that is, set in gold, that you cannot go against this. Maybe there are ways around this, but my point is that's certainly something to pause and think about. And just so you know, this is sort of a heuristic argument for the TCC, but in my mind, the more sophisticated argument is actually about non-unitarity, which is due to a time-dependent Hilbert space. So we have more and more modes becoming a part of the system Hilbert space at late times. And I will talk about this much later on, so I don't want to spend time right now. This was noticed by Weiss in the 80s and Ted Jacobson in the context of black hole physics, but also he has a section in this paper about cosmology, that why this non-unitarity is a big problem. So this is sort of the same problem with this trans-Planckian physics, but maybe the more refined version. This is more the heuristic version. So the TCC was just to say that, okay, we won't worry about what kind of UV theory should describe this trans-Planckian physics, because we don't know, we don't have one yet. But let's just say that even if they're trans-Planckian modes, they should never cross the horizon so that they never become part of our observations. So it's somehow analogous to Penrose's cosmic censorship hypothesis, because it's just saying that there may be trans-Planckian quantum fluctuations in your theory, but they better be hidden behind the Hubble horizon. If they never cross the horizon, they never become part of our observations. So that's what the TCC does. So just diagrammatically, what does it do? So the TCC does this. It says that, look, inflation's biggest success is that the scales that we observe today in the sky must have come from within the horizon to begin with. But the TCC tells us that now let's take a Planck length fluctuation. That one should never cross the horizon. That should just about cross the horizon. So that's the maximum amount of inflation you can have. So you have sort of a hierarchy in the amount of
Excuse me?
you can have, right? Yes, go ahead.
Can you hear me? I'm sorry, I don't understand this reasoning actually, because it seems that you are pushing inflation towards a cutoff that you should not cross in order to trust inflation. So of course you will run into some troubles, and then somehow the solution to say that those modes should never exit the horizon, I mean, seems a bit weird to me. Why don't you just say that inflation doesn't work and you have to have something else at those energy scales?
Right. So my point is just that if inflation doesn't work at those energy scales, then this mechanism better stop at those energy scales. That's what I'm saying. So the stretching due to inflationary cosmology must stop for a Planck length fluctuation. That's what I'm saying. I'm not claiming that inflation should explain trans-Planckian physics. I'm saying that there is some other theory. It might be that there is a UV theory which very well describes things here, and then at this scale switches on inflation as the low energy theory at that point. That can happen, but we don't have it yet. So all I'm claiming is that, let's say at this scale, you shouldn't have inflation, so much inflation that these kind of scales get out of the Hubble horizon.
Okay, I'm just not sure why you can say that those scales cannot exit the horizon. If there is no inflation anymore, then I guess you can have many other things.
Yeah, the point is, this is a hypothesis, right? Let's say this is just a hypothesis. So okay, if you're not happy with this, that's okay. But I'm just, let's assume this and see where we go. And then I will try to justify this from other things.
Okay, thank you.
Okay, so this just tells us that now you have a hierarchy in the amount of inflation that one can have, right? Like you must have a certain amount, otherwise inflation loses its crowning glory, and it cannot have too much, because then there's this TCC problem. I mean, if you believe in the TCC. Okay, so what does that tell us? So that tells us that there is a hierarchy for n, the number of E foldings, and because there is a hierarchy, we can find an upper bound on the energy scale of inflation, which is extremely small now, which gives, I mean, if you assume now further that this is single scale, single field inflation, this gives very small values for epsilon and r. So, the good thing is that now we know what is the spectral tilt from observations. So if epsilon is this small, then eta has to be this large. That's kind of nice because if you remember the de Sitter conjecture that said that one of these two things has to be large. Okay, 0.02 is not very large, but it's large compared to 10 to the minus 31. So at least one of these two things is ensured to be large just from observations. And that's kind of nice with the de Sitter conjecture. And this generically tells you that Swampland favors hilltop models. I mean, again, this is just single field models. Of course, you can do a lot more with multi-fields and things like that. So how do we evade this bounds on R? So, if you ask Robert, I guess he would say that, no, this is part of predictions of inflation. And this just shows you that if you ever measure R, that rules out single field inflation, at least, if not inflation, because he doesn't like inflation so much. But on the other hand, you can obviously have you can invoke some alternate mechanism for production of primordial tensor modes, as I showed in this paper, and you can still have a much, much larger R, which is still compatible with TCC. But even then, even if I can find an R and so on, if you have this kind of low scale hilltop models, they have extreme fine tuning of initial conditions. So there's a problem with this kind of models of inflation. So can there be a way out of that? And turns out that if you again choose some non-perturbative quantum gravity theories, such as this tunneling wave function due to Vilenkin, you can actually get the initial conditions that one wants to start at the top of the hill. So this is not saying that any of this is sacrosanct. This is just saying that actually this question is a good one. That maybe there is some UV theory which allows you to still have inflation, and in that coming from if you believe in the tunneling wave function to be the fundamental theory of the universe or whatever, then this initial conditions are not at all fine-tuned. These are the natural initial conditions. So this is just saying that the TCC seems to have some obstructions for UV completion of inflation, but it doesn't really rule it out. There can be still some UV theory which comes and saves the day. There is also this argument made recently by Cliff Burgess and collaborators that maybe the Transplanckian modes becoming part of the observable macroscopic modes at late times is not a problem for EFT, if at least this evolution is adiabatic. But what we found in a completely different context is that actually, even though slow roll inflation is adiabatic, the beginning and end of inflation typically, in this paper, we just looked at a particular model of renormalizable potential. But in that model, the beginning and end of inflation actually requires some non-adiabatic physics. It actually requires some non-adiabatic evolution. So this is not such a small approximation to say that this is adiabatic. If it is adiabatic, these people claim that the TCC is not required. The Transplanckian modes is not a problem. They did not say that the TCC is wrong. They said that it's probably not so much required. And my point is that there are certainly models in which non-adiabatic physics is important to both for setting up the initial conditions for inflation as well as to end inflation. Anyway, so since I've already been asked this question, and this is my last slide on this kind of things, how long did inflation last? That's the question which we want to answer, right? There seems to be a motive here that the Swampland conjectures are kind of sort of telling you that inflation couldn't have lasted very long. So we know it must have lasted a certain amount to explain data, as I just said. But this can be us. If inflation lasted a very long time, this can be us. And there might be much bigger volumes, much beyond our own Hubble patch, right? So is it this, or much, much bigger? So is there an upper bound to the amount of inflation which we could have had? That sort of seems to be the theme of the Swampland conjectures with inflation, at least the theme that I choose to focus on. So just now, this was a good question which came up that, why should I believe the TCC? It seems like sort of ad hoc. It is a hypothesis. I'm not, again, claiming that any of this is rigorously proved from some fundamental axiom or anything like this. But there seems to be some deep structure. For example, the TCC implies the de Sitter conjecture, but also the TCC, as I showed, I think 2 years ago now, almost 2 years ago now, that the TCC itself can be derived from other aspects of string theory. So for example, this argument that I gave you was sort of an EFT argument, right? That you have some wavelength and it's stretched, and then Planck length wavelength should never be stretched so much. But what if we can derive TCC without going into anything about EFT on accelerating spacetime? We start with this distance conjecture when we use this species bound, and I won't give the details, and we come up with TCC. Then there is some reason to believe in the TCC. And since then, many people have tried to find versions of the TCC. So it's not exactly the TCC, neither did I find exactly the TCC, but some refined version of it. So with some order 1 numbers in front. which were found to follow from the gravity conjecture, the scrambling time of de Sitter, or maybe entropic arguments and things like this. And also with Arjun and Jaime, we also showed another refined version of TCC to follow. So another part of this is this no eternal inflation principle. So what we actually first showed was that if you assume the de Sitter conjecture and you say that I want my theory to be under perturbative control, so S3 over S2, the cubic Lagrangian should be smaller than the quadratic one, that would rule out stochastic eternal inflation. So the de Sitter conjecture actually rules out perturbative stochastic eternal inflation. And this was turned into sort of a principle by Tom Rudelius, who quite independently tried to formulate eternal inflation as Fokker-Planck equation, and then showed that for most potentials, in fact, for all potentials actually, they seem to be in tension with Swampland. So there seems to be tension also from Swampland and eternal inflation. And as I already mentioned, Alan Guth back in 2006 had already told us that inflation is certainly not eternal into the past. Even if there was eternal inflation, it's certainly not eternal into the past. An inflating region must have a past boundary. So it seems at least we can agree on this, that inflation must have a finite beginning. It can't be semi-infinite in the past. What we can quibble about is how long can inflation last? TCC puts a very stringent bound and says that inflation can last only this very short period of time, and that seems to be very strong. Even if you don't believe in the TCC, there are multiple indications which seems to suggest that there is an upper bound, which is also, as I mentioned, from this calculations of entropy from de Sitter space and so on, which seem to suggest that there should be some upper bound on the duration of inflation. And that's a takeaway message, that not just from quantum gravity principles, but also from QFT principles, there seems to be some upper bound on the duration of inflation. What this upper bound is, I will try to say in the rest of the talk. So I'll just stop here for questions. Sorry. Okay, so since there are none, let's come to one of my main themes today, which is inflation as an open quantum system. So how much time do I have, Cyril?
20 minutes more.
Okay, good. So are there any lessons for UV completion? Just now I forget all about quantum gravity. I'm just looking at inflation as a QFT, but as an open quantum system. So, okay, why open quantum system? And I should mention, although this topic is much less studied compared to how much people have studied inflation, there's a lot of people who have still studied.
Sorry, I have a question.
Sure, go ahead.
Hello. When you say open inflation as a open quantum system, unfortunately, I don't understand really what it means, because inflation is not a system. Inflation is a model. Therefore, can you more precisely define what do you mean by inflation as open system?
Yeah, I mean, this
is
going to
as open system, because inflation is simply a model.
Yeah, this is going to be, this part of the talk is entirely about this. So if you're not happy after this part of the talk, you can just ask me again. So I'm going to define what open system means for inflation and so on. That's this part of the talk. Okay, so there's a lot of people who have worked on such things, and let's see. So what can we find? So can we find some new quantum effects for inflation, just treating it as this open system? And I will define what open system and open EFT and things like this mean. So of course, this goes back to stochastic inflation formulation that we usually tend to write the background as classical and fluctuation in quantum. This is not very satisfactory from theoretical point of view. And this was replaced by stochastic inflation, which says that the super Hubble modes sort of source the background. And decoherence also requires that decoherence is essential for quantum to classical transition. I already mentioned that classical perturbations originate from quantum fluctuations. How did the quantum to classical thing happen? Decoherence must be required. I mean, must have happened at some point. And decoherence requires that your observable system is part of a larger system. Your observable modes are part of a larger system. So it must be interacting with some environment. And in this sense, I mean that the observable modes during inflation must be part of some larger environment, larger system, which has an environment. So why does usual EFT not apply directly to inflation? What happens? I mean, we always know how to do EFT in standard particle physics actions. What's going wrong there? So the usual process is that in particle physics actions, if you start with low energy particles, you will always end up with low energy particles. You can never have, if high energy particles were absent to begin with, they will not appear, because that's just because the integrated out degrees of freedom are excluded by some conservation law, in that case, energy conservation law. In this case, this is not true. The integrated out, or the things that you trace over your environment, those degrees of freedom are not excluded. And this is heuristically very easy to understand, right? So you have a mode which is, let's say, sub-Hubble, and which is part of your environment. At some point, it will become super Hubble, and it is not excluded. So in this sense, the system degrees of freedom can exchange energy with environment modes. And we need this open or out of equilibrium. I don't know really the difference between these two things, to be honest with you. I just found people use different names for these systems. So I will use OpenEFT. We will need to use something like an OpenEFT to describe the observable modes during inflation. And that leads to some non-Hamiltonian evolution. And I'll explain why it leads to some non-Hamiltonian evolution. And this non-Hamiltonian evolution, or this non-unitarity, usually builds up quantum entanglement. And can this quantum entanglement somehow show up in observations? That's kind of what I'm going for. That's like the big goal. I'm not saying I'm there yet, but that's a big goal. So there's a lot of interesting aspects to it. Of course, entanglement is quintessentially a quantum phenomenon, right? Like you cannot fake entanglement with classical degrees of freedom. So this can be a smoking gun for the quantum origin of structure, specifically for inflation. So people have already, come up with different ways of these cosmological Bell inequalities, or even looking at the pole structure of the bispectrum very recently. So all of these were designed to discriminate between a model which has some classical stochastic initial conditions as opposed to having some really being sourced by quantum vacuum fluctuations. So this seems to be another very interesting way to do that. If we can find some observable signature of entanglement, that would discriminate, that would prove that inflation does have a quantum origin, in the sense that inflation fluctuations have a quantum origin. But of course, this is not exclusive to inflation. There are other phenomena as well, like, for example, like pyrosis, which also has a quantum origin. So all of these things that I just told you should also apply to those things as well, those scenarios as well. And I will give you an example in a short while. And just to mention, this is not so crazy. Like what I'm saying is not so crazy. Like how can you you can think that how can you possibly observe quantum entanglement in the sky? It's not really that crazy, because as Vincent Venant and Jean Martin showed us, that decoherence does affect observations. I mean, it just doesn't suppress the off-diagonal terms. It really affects bispectrum and trispectrum and things like this. So it really affects observations. So there's no reason why entanglement cannot. So this is not just a conceptual thing that we should use open systems. It can have a really big role to play for observations, the predictions for inflation. Okay, so now let's see what kind of an open cosmological system am I talking about? And that was, I think, the question about. So I will just take vanilla slow roll inflation. So it's like really what is known as single clock models, nothing fancy. I will consider the short wavelength modes of the same curvature perturbation field to be the environment of the long wavelength system modes. And the coupling between long and short modes will be provided by the leading order cubic nonlinearity arising solely from GR. What does that mean? That I'm going to look at the cubic action, which comes just from the nonlinearity of GR. I'm going to take its leading order term, and that will be the coupling between long and short modes. Any additional field, you can then say that, okay, but why are you doing this? Because any additional field, like now if you choose to have, let's say, one more field, which is very natural for inflation to have at least one more field or a couple more fields, that would lead to extra couplings between the inflaton field and those fields, and would lead to more entanglement. So that's just saying that we are trying to find somehow like a lower bound, because if you have, this must be there, right? You must have one scalar field, and that must have short and long wavelength modes. And you must have cubic nonlinearity just from nonlinearity of GR. So that's the non-Gaussianity that I'm looking at. But any additional field will lead to more of this effect. So that will magnify our findings. You can even think that why GR? You can have some low and some higher curvature theory, but as long as its low energy limit coincides with GR, that will again magnify things. Also, you can have different interactions. I mean, indeed, it might be more natural to have interactions such as DBI or have non-minimal couplings and so on. And that will again enhance our results. So those are interactions which we know give observable amounts of non-Gaussianity. And if we choose something like that, which has like an FNL, which is not zero, which is the case for for this vanilla slow roll models, then that would be very nice for us, because that would really magnify our results. So I'm trying to do the simplest thing possible, which would give us like the lower bound on such kind of effects. And finally, I will also assume that they're in the Bunch-Davies vacuum. Again, if we choose some excited states, again, that will strengthen our conclusions. So just this diagram, like, to make this, which all of you know, that these modes kind of leave the Hubble radius, and then they become part of this system modes. And that's how also, that's the similarity with stochastic inflation, as I mentioned, at least heuristically. I'm not deriving the equation, but heuristically. And this is the system. Like, we have a band of environment and system. And I assume that there is some UV theory. For this part of the talk, I'm not going to go at all into what kind of UV theory should be there or what properties it should have. I'm just assuming that we would someday figure out how to deal with this, and normal renormalization works on this surface. And this is the Hubble horizon, which demarcates my system and my environment. And that's the theory that I want to study. And if I can do that, I will find a universal lower bound on the effects of entanglement. And this would also be somehow like an indirect signature of cubic non-Gaussianities, right? Because if you remember, for single clock models, FNL is actually exactly 0. It's unobservable. That was shown by Zaldiaraga and collaborators, I think, in this Gaussian normal Fermi normal coordinates. But this would mean that those are still there. That's what leading to this interactions between different modes. And that's what leading to entanglement. Okay, so I'll go through this very quickly because I'm sure all of you know this. For primordial cosmological perturbations, if we just look at the quadratic action, we have a usual scalar field piece and a squeezing piece. And when this term is bigger, that means you have super Hubble modes, they're in the squeeze state. And when this term dominates, the Hubble modes are in the Bunch-Davies vacuum. The quantum vacuum unitarily evolves. So I already talked about non-unitary dynamics. So just to mention that there's nothing non-unitary at the quadratic level. It unitarily evolves into the squeeze state. As all of you know, I'm not writing down the formula for the squeeze state because it's horrible to look at. And you just write the product state to be the squeeze vacuum. Okay, so what are the gravitational non-linearities? And I think there's a typo here. Sorry for that.
Excuse me.
Yes.
I have again a question. Yes. From the quadratic action that you wrote down, you see that there will be time derivatives of the scalar field, for example. And these ones will lead to a quadratic, actually, coupling between the environment and the system, as you call them. And so
there is no coupling.
This is the usual setup
So here there is no coupling, right? Because there is no coupling between modes of different k. Just k and minus k are coupled by the squeezing term, but there is no coupling at this time.
But at the exact scale of the cutoff between the long wavelength and the short wavelength modes, there is an interaction.
Right.
So this will lead to a quadratic interaction, actually. And that's the usual approach of stochastic inflation, to consider the quadratic interactions.
I see what you're saying. Yeah, so that's not the interaction. Okay, now I understand your question. So yeah, that's not the interaction that I meant. I'm going to look at the cubic interaction. That will be my leading order interaction that I look at.
Yes, but why? I understand, but why?
Because I'm going to calculate the entanglement entropy, and people have already calculated the entanglement entropy corresponding to the squeezing interaction. So that's already known. And I will talk about that at the end.
But wouldn't you expect the quadratic one to be dominant?
It isn't. And I will show you, I mean, that answer is already known, and I will show you that it isn't.
Okay, thank you.
Yeah. Okay, so now let me look at the gravitational nonlinearity and this cubic action. And this is, again, not very nice to look at. And this is the leading order term because, zeta freezes outside the horizon. So I will just look at this. So just to give you, again, not to go into too many details, mathematical details, but just to give the overview. So what's different with flat space QFT? So what role does gravity play? So there are three things that I, at least for my purposes, would identify. One is that it acts as this pump to give me zero momentum correlated pairs. That's the job of the squeezing because I have a time-dependent background. I have a time-dependent mass term for the harmonic oscillators. And then there's the co-moving Hubble horizon, which acts as a natural scale, demarcating the long and short degrees of freedom. So that gives me a natural scale. I don't have to assume some fiducial scale demarcating my system from the environment. And then the cubic action provides me this interaction term that I look at. I mean, I'm ignoring the squeezing interaction for purposes that we will see later on. So the Hilbert space I can write like this, and this is just the Fock spaces, the product space of the Fock spaces gives me the system mode, and similarly for the environment. And the full Hamiltonian is, I just write down the quadratic Hamiltonian for the system and the environment in terms of this limits, and then the interaction Hamiltonian is this one. Of course, I need to write all of this down in terms of these ladder operators, but I mean, you can already see that how big the expressions are for quadratic, so the cubic one I won't show you. And now let's go to calculate the entanglement entropy of cosmological perturbations. So this slide is just the generality, like how people do this. And what I'm interested in is to calculate the, I look at this paper because they calculate the entanglement entropy in momentum space. That's the thing which is important for me for my inflationary calculations. So I'll just give you the brief overview again. You have a Hilbert space factored out in system and environment, and you have a Hamiltonian that looks like this. You have a free vacuum, let's say, which looks like this. So this is the free vacuum for system product with the free vacuum for the environment. And then the interacting vacuum can be written like this, where, and then finally the entanglement entropy, leading order entanglement entropy looks something like this. Again, I'm just copying this from this paper pretty much, where these ends are the end particle state of the system, and similarly for the environment. And these are the energies corresponding to the ground state and the nth excited state, so to speak. So I did not write the plus dot dot dots. So the plus dot dot dots would be like leading, I mean, this would be like higher order terms in perturbation theory. So what goes into this calculation is like really calculating some matrix elements, and the way that this matrix element was calculated was using standard time independent perturbation theory. That's how this factor appears in the answer for the entanglement entropy. Okay. So I didn't obviously go through this in any detail, but let's just say you trust me, and if you don't, you can just go to this paper to calculate or see how entanglement entropy comes out just for scalar QFT in Minkowski. So there's nothing fancy here. So what do I need to do? Again, I won't show you the details, but what do I need to do different for curved spacetime? So first of all, the proper state for the system modes now, the environment modes is still in the quantum vacuum, but the system modes are in the squeezed vacuum. So again, see, this is just the free vacuum part of it. So of course, I've still assumed the squeezing interaction, as someone pointed out, but I haven't assumed the cubic interactions yet. So now we need to do some time-dependent perturbation theory, because the interaction parameter itself is time-dependent. There's some scale factor which appears here. And because also there is no well-defined notion of the energy. So if I go back to this equation, you see the energies appearing here. So there are no well-defined notion for the energy for the squeeze state. So what do? Well, luckily, we don't really need the energies. We really need the energy difference. That's written menta. But there are some subtleties as well. I don't want to go into details, but just to tell you what kind of subtleties can appear. So for example, an annihilation operator acting on the Minkowski, acting on the usual Fock vacuum gives you 0, but on the squeeze state or the squeeze vacuum doesn't give you 0. And this leads to new interaction terms which has to be considered. So typically for calculating the entanglement entropy for flat space, these are the kind of terms that you need to consider for the matrix element. But now you need to consider terms which go like this. Because the CKs, if they belong to the system mode, then they will hit on the squeezed state, and that won't annihilate it. So an illustration of this is like, typically, again, for flat space, if this was not squeezed states, but just 0, the usual Fock vacuum, you would have 1 here, roughly speaking, up to factors. But now there's some sinh squared, there's some squeezing factor appearing there. And that's just a quality of, time-dependent backgrounds and inflationary backgrounds. And as we have shown in this paper, the squeezed configuration. So when you have 2 UV modes and 2 environment modes and 1 system mode, that's the configuration which dominates in this entanglement entropy. Again, you have to trust me on this because I'm not proving this. And what's the result? So up to order 1 or up to like small factors, let's say order 1 factors, this is the entanglement entropy per unit physical volume that we find. So interestingly, you find some factors of mass Planck, we find some factors of the Hubble parameter, which we assume to be constant during inflation. But what we also find is that there is this expansion factor. So the AI is the scale factor when inflation started, and A is at whenever time when you calculate this entanglement entropy. So that's very nice. Like if you calculate this at the end of inflation, then this gives you like some dependence on the duration of inflation. Okay, so there was a question on this. I will skip this slide because I think I'm running. Have I 10 minutes, something like this, Cyril?
I said 5, please.
5, okay, good. So I will skip this slide, but just to say that one can calculate the squeezing entropy. People have calculated this earlier. We used a different approach. We used this approach where we choose a coarse graining. We ignored the off-diagonal terms, and we ended up with a result which matches with previous answers. So this was the result that we came with, and the question was absolutely right. There is an entropy corresponding to this squeezing, and that can be that is given by this number, and it can be approximated to be like this if we assume that there are no modes at the beginning of inflation, which is super Hubble. Okay, so the squeezing entropy matches results. As I mentioned, there's a lot of people who've calculated this earlier using different approaches, and our result matches that using the coarse grading that we did. Interestingly, unless we take n to be very fine-tuned, to be extremely small, the entanglement entropy actually wins over the squeezing entropy. So that's very counterintuitive, as was also pointed out by whoever asked me the question, because you would expect this quadratic action to give you the bigger entropy. But this kind of things happens. Like I remember in this decoherence paper, I think Jean Martin and Vincent Venant showed that you can actually have a situation where the trispectrum is bigger than the bispectrum due to for the contribution of the decoherence part. So something like this is also happening here, that the interaction effects, and please correct me if I'm wrong, because I know you guys are in the audience, but something here similar is happening here, that the entanglement entropy, once you let inflation go for a little while, it actually wins over. To begin with, yes, it's very small, it's smaller than the squeezing entropy, but with time it wins over. And this is because entropy is not sort of linear in these variables. And now if we further assume that the thermal entropy produced during reheating is greater than in this entanglement entropy, we find a bound like this on the duration of inflation. So I want to be very clear, this is an extra assumption, right? Before this, we just calculated the entanglement entropy of cosmological perturbations during inflation. But now if we assume that the thermal entropy produced during reheating is bigger than the entanglement entropy, we get a bound which looks awfully close to the bound from TCC. And this is, of course, we need an additional assumption, but maybe you can justify this. If you are a fan of the TCC, you can justify this from perspectives of the graceful exit, that all the entropy that we see, because all the particles were created during reheating, all the entropy that we see should also be created during that, and second law and things like this. But surely this is an extra assumption. And just one point to make on this is that this is more general than inflation. We can calculate the entanglement entropy for something like ekpyrosis, because that also has a quantum origin for fluctuations. And we did that, and we again assumed that the entanglement entropy is smaller than the thermal entropy during reheating for ekpyrosis. And we find that in that case, it puts an upper bound on the energy scale of the bounds. And we showed that in this paper. So in that case, it doesn't say anything about the duration of ekpyrosis, but it says that at what scale can the bounds happen? So that's nice, because you want the bounds to happen at really high scales if you want to have ekpyrosis from string theory or some quantum gravity theory, and it puts a bound on the upper, on the energy scale of the bounds. Okay, so let's say I have, I will say 3 minutes, and in 3 minutes, let me try to say, so this was all nice, but this is kind of sort of saying that entanglement calculations tells you that the duration of inflation is constrained, and seems like if you make some additional assumption, it can look very similar to TCC. I should also say that when we started this calculation, our hope that we would find something like the entanglement entropy wins over the squeezing entropy. That was what we were going for. We had no hope about TCC. We didn't even think about TCC. But after we calculated the entanglement entropy, and we said like, okay, what happens if we just say, if we put this additional assumption, this just popped out. This is not at all like, we never envisioned something like this happening. But can we see something more? Can we get some corrections of power spectrum? So in like 3 or 2 minutes, let me try to convince you that maybe we can. So as I already mentioned, if we can find some detectable effects, that would prove the quantum origin. It can even, as I also mentioned, like for ekpyrosis, it would give me some other detectable effect, right? So this would be good. If we find some detectable effects, that would be also not just prove the quantum origin of inflation, but maybe distinguish between different paradigms. And as I also mentioned, for single field, vanilla slow, single clock models, FNL is 0, it's unobservable. But this will be sort of an indirect signature because the coupling is happening because of this cubic non-Gaussianities. So what's the story here? The story is that, of course, the non-unitary dynamics is coming out because where part of the Hilbert space forms your system modes. If you take the full Hilbert space, there's nothing non-unitary here. There's no quantum gravity, some quantum gravity weirdness. It's because the full density matrix is obviously following some unitary dynamics, but we trace out over environment modes, and then the system modes does not give you Hamiltonian evolution. It gives you Hamiltonian evolution plus some Lindblad terms. And these Lindblad terms are these dissipative terms which sort of encapsulates losses and gains from this environment. You can dump energy from the environment, you can gain some energy from the environment, and that's why this is not Hamiltonian anymore. And actually, people have shown in the 80s that these Lindblad terms can be made to be equivalent to adding new Hamiltonian terms with randomly varying sources. So maybe there's some connection to stochastic inflation formalism there. Again, I'm not an expert on this. I'm not claiming that I'm proving any of this. This was from a very old paper. And the cosmological setup, we'll keep the same cosmological setup. We'll work in this interaction picture and we'll solve the master equation perturbatively. So I won't go through the details. Let's just say that we have some master equation. We use some typical assumptions like Born approximation to solve for this density matrix, the reduced density matrix of the system. And we finally end up with a power spectrum. Okay, so this is the general formula for getting the power spectrum. At 0th order in the approximation, we of course get back the scale invariant power spectrum that we all know inflation produces. And the first order correction gives me a term that looks like this. So it goes as epsilon h squared over 2 mass Planck squared, but also with the number of E folding appearing there. And there's some prefactor which sensitively depends on all these complicated integrals that we carried out with Jaime and Aljun. Okay, so let me show you a couple of plots. So as if I choose n to be, let's say 10 to the power 2, I can choose n to be much bigger, but if I choose 10 to the power 2, this is the corrections to the power spectrum and to the ns minus 1, to the running, to the spectral tilt, and so on. But what's the final say? Because I'm running out of time, so this is my final slide. So the first order effect is a result of both dissipative and radiative corrections. You might think that this is just loop corrections. This is not just loop corrections. Although you could have guessed this factor by power counting from loop corrections, maybe even this factor from loop, but it's not so straightforward in this case, the NC square factor, the number of E-folding factors. But the scale dependence is very different. For loop corrections, if you go back to this classic paper by Weinberg or other papers, there is a log Q scale dependence of the quantum correction, whereas here, this is not the case. And remember, we did not choose any specific form of the potential. Of course, those are hidden sort of in the epsilon and etas and so on, but we did not need to choose any specific form. This is a combination of dissipative and radiative corrections because we have to use the kernel, which is like a loop, but with legs with different time, but also dissipative terms like the Lindblad terms already play a role. But this also gives me an upper bound on inflation, right? And of course, this bound is much, much bigger. This tells me that the number of E-foldings can be 10 to the power 5. That's just because this bound comes from the fact that this correction term is not as big as the tree level term. So that's just a perturbative term. So this is there. On one hand, this is a much larger than TCC and this other bound that I talked about, but there's no additional assumption. This is just saying that as long as we're in perturbative regime, this bound should be true. So at least it tells me that inflation must have some bound. And if it's a reasonable high scale, maybe this can be potentially detectable and so on. I won't go through this. And one nice feature is that the ns minus 1 and its running, so this alpha parameter, this running of the tilt, both of these things increase with the number of E-foldings. This is typically opposite for single field models. They decrease with number of n's. If you increase n, they decrease, but these effects due to this non-unitary evolution actually increase. And I just mentioned this, you can think that maybe epsilon can be made very small and then this term just goes away. That's not true because as I already mentioned, one of epsilon or eta must be large. And although I always work with a specific kind of interaction term, there's another term which looks exactly the same, but instead of epsilon squared, it is epsilon times eta. So this is again, in some sense, again, sort of a lower bound. Okay, I will leave the discussions, I'll leave the discussions here and I will stop here for questions. Thank you.
Okay, thanks, Shlo. So are there questions? Okay, I guess there are.
Yes, I have a small question.
Sure.
Oh, sorry, maybe let me put the video. It's actually related to one of your last points in comparison to loop computations. If understood correctly, you were comparing to the result by Weinberg, 2005 and so on, but precisely, you mentioned Senatore, Zalerga in different contexts. I mean, they showed that his result is wrong about the fact that the correction goes like with log of k. So basically he was saying that loops were inducing a scale-dependent correction. And well, there was a mistake, and it turned out to give an unobservably, if you want, numerical correction to the power spectrum. So it's very similar to what you find, which is just a number correcting the power spectrum. And so I'm wondering whether there can be actually a link, given that also one of the claim or thing that people envisage about loop correction is that it can make the power spectrum grow with time, precisely with logarithm of the scale factor. But after careful study, people understood that no, actually the power spectrum, even with loops, doesn't have this secular growth. So I just wanted to make this point about at least the paper by Weinberg, but I'm happy to know more.
Yeah, so you're absolutely right. So as I said, so the scale dependence, yeah, maybe it's not there. I know there's some controversy, although I don't claim to be an expert on this. But for me, actually, in the beginning, I would have just said that the main correction is that you have this n squared term. So this really grows, as you said, like this kind of the secular growth, right? So this is like this log a kind of term. And this really grows with the number of e foldings. And that's really a fact that you can intuitively understand this in our calculation, because at late times more and more modes are part of your system. So you have more and more modes which are coming in, dumping in from nowhere, whereas the number of modes of the environment is actually fixed, because the environment loses some modes to the system, but it's also gaining some from the UV region, so to speak, right? So the point is, it's simple. It's sort of intuitive why this n squared term should be there. That's why I said, like, because Weinberg said there's this n squared term, so I did not want to say that you can never get this from loop corrections. But I said this is much less straightforward, because I know there's some controversy about this, like whether you can really get this n squared factor. So if indeed the point is that this n squared, this kind of log a term should not appear from loop corrections, then that makes me happier. I don't care about the scale dependence anymore, because this is clearly the distinguishing feature. The distinguishing feature is that there is not just this kind of power counting term, but also this n squared term.
Okay, I'll have to think more. But just even just for the audience, I mean, there's not anymore any controversy. I mean, there was a mistake. And it's
right. Yeah. No. Sorry. I mean, I believe you. Yeah. My point is, the reason is this is not a loop correction, because we are looking at some of the kernels. In fact, even in the kernels, we're like really looking at some specific contributions. So, like, for example, we're looking at 2 environment and 1 system mode. We're not taking into account. So to do a proper loop correction, you have to do 2 environment, 1 system, 2 system, 1 environment, all the permutations. We're just looking at the leading order term, and that gives me something like this. So this is not a loop correction, so I'm perfectly happy that this result is different.
Okay, thanks very much for the
questions. I can't see anybody raising his hand, so I'll wait a few seconds just to be sure nobody has an additional question. So
actually, I have one.
So go ahead for the last question. Yes.
Merci, Cyril. So my question is about the bound that you get on the duration of inflation from the last part of your talk. Mm-hmm. So first, I'm not even sure to understand the reasoning, because you say that you want to have a perturbative calculation, and that sets an upper limit on n.
Right.
But that's mostly a limitation of your calculation, which does not go in the non-perturbative regime. So am I right? I mean, is there anything physical that prevents you from having a non-perturbative regime?
No. I mean, this is similar in spirit. Like, for example, a lot of people have calculated, bounds for eternal inflation, for stochastic eternal inflation, but perturbative bounds. And that, of course, you can say that maybe eternal inflation, that it goes outside the perturbative bounds, and for that reason. And here also you can claim that, there can be some non-perturbative physics. And I'm not claiming that that's not true. I'm just saying that within perturbative physics, there is a bound that you get for inflation. Yeah, that's a statement.
Okay. Because it could, I mean, the parameter alpha, can you remind me where it comes from?
Yes.
Could it be extremely small? I mean, and then you have no bound at all on n?
Yeah, you can. So for example, so that's what I was mentioning. So there are different ways of making this small, right? One is to say that epsilon is very small, and that doesn't work. That's what I was saying, because see, the reason why you get epsilon here is because I chose a particular kind of interaction term, which comes with this epsilon square, zeta square, zeta partial zeta square. But there is an exact similar term which goes as epsilon times zeta. And usually this term is taken care of by field redefinitions, as Malvasena did it. And that's not important for correlation functions, but actually that is important for calculating loop corrections and things like this. So there's an exact similar term with epsilon times eta. And if you make epsilon very small, what would mean is that the epsilon squared term is not the leading order term anymore. Your epsilon times eta term is the leading order term. That's just because you can't have epsilon and eta both to be very small. My bounds were all assuming that epsilon is 0.01. So one of those two things have to be 0.01. Because if they're not, just ns minus 1 from those observations, you know that one of those has to be small. The other thing you can do, of course, is you can say that the scale of inflation is very, very low. That you can do. And if you do that, then of course, this bound sort of goes away. But then if the scale of inflation is very low, for low scale inflation, there's a lot of problems. Like as I already mentioned, like, there's this fine tuning problems and so on. And in some sense, if you have low scale inflation, then you are back into this TCC regime. So that's probably not what you want to do to avoid a bound which is not so stringent anyway. You don't want to reduce the energy scale of inflation too much.
So
but yeah, you can.
I can't see anybody raising his hand unless I'm mistaken. So there are no questions. So let's thank Shudo again for this talk. And I remind you that there will be no seminar next week. And so it will be only in 2 weeks that we'll have another seminar.